Hello everyone, welcome to our session where I'm going to explain how to decrease FME runtimes through AWS Elasticity. But first, let's introduce myself and my colleague. I am Maxime Hughes, Principal High-Performance Computing Specialist SA at Amazon Web Services. And with me, my colleague Scott Batman, who is Principal Solution Architect at Amazon Web Services as well. So you're probably familiar with the view of FME on-prem, where you have your corporate data centers, an FME desktop servers, or a couple of others that are connected to an Oracle database where you have your spatial data and a file system. And all of this is a fixed capacity of processing. So your processing can take hours to days because you have a limited amount of machines. And also, this hardware is provisioned for peak capacity, meaning like you have this hardware going to consume it for a certain period of time. There is not flexible toward like can you change it or share it with other people as needed. So what about using the cloud for this processing? And what is the value of doing this type of processing on AWS? Well, first of all, you have the ability to experiment quickly because you have a various choice of instances. We have 400 and plus Amazon EC2 instances with Intel, AMD CPUs, GPUs. So they give you a broad choice of hardwares, but also a broad choice of price and a broad choice of performance that you can pick. And you can adapt that when you need it. Because on cloud and AWS, you pay for what you consume. So you can create those instances, use it, and deprovision it, and you only pay for what you have used during this time of the processing. In addition, you can increase the number of instances you need, meaning like the number of computing nodes you are going to need, or your FME engine you are going to need, and they grow as the demand of more computation you need. And then when you are done processing, it is shrink down as needed. In addition of that, you have access with AWS with the global infrastructure available in one click of deployment in multiple regions in the world. And you have access to a capacity of compute that is virtually infinite. But how you do this? What are the key features of FME to use FME elastically on AWS? Well, first of all, you're probably using FME engine licensing. So in the cloud, what is very advantageous is to use FME server dynamic engine licensing. It is a computation-based license, meaning it is consuming hours when the FME engine are processing. That allows you to meet the demand. It's not capped for maximum utilization, but the license is to one number of hours. So you can increase the number of engine as you need it and then turn it off when you have no computation at all. So they give you great flexibility. And below you can see an example of dynamic engine instances when you clearly see this is per hour, minutes, and second of the FME engine running processing. And you can have an almost unlimited amount of dynamic engine that it can do processing for you, reducing the computing time. Now you are maybe wondering how I can do that on AWS, how I can set up the FME dynamic engine. Well, let me go walk through an FME HPC architecture walkthrough where we're going to explain how it is designed. So you can start with an Amazon Aurora already set up, a database, a special database where your data are. And through a cloud information deployment, we will set up an Amazon EFS that's going to be acting as a shared file system where the FME repositories or resources are going to live. And they're going to be shared across an FME servers and FME engines. Then an FME server is deployed, and as I explained, is going to be have access to the FME repositories and resources, and additionally the workflows. Then you have an auto-scaling group that hosts the FME engines. You cannot hear that this auto-scaling has 0 FME engines, meaning like 0 capacity of computing. Then we added the Python daemon that is scanning the queues on the FME servers and it is detecting if there is jobs that are queued to be executed. And this daemon, after a certain amount of time, when the job are queued, 10 minutes in that case, the Python daemon automatically increase the capacity of the auto-scaling group, adding additional FME engines and adding additional compute capacity in order to process the jobs. Then, when the FME engines have no longer jobs to be needed, after 5 minutes, they self-terminate if no job or running jobs are assigned to them. And then we go back to the initial picture where you have no FME engine at all. So you're not paying for hours that don't go into processing, it is terminated, and you are not paying for extra capacity. Let's talk about the various ways that you can use AWS and different type of pricing you have. So you have the reserve instances or saving plans that allow you to minimize the amount of compute. That's a commitment of compute that's going to do through a 1 year or 3 years commitment. In addition to that, you can use Spot. Spot is the unused capacity on AWS, and you can save up to 90% compared to on-demand pricing. In addition to that, you have on-demand pricing, that is on-demand instances that are steady and available for computation. For the FME and elasticity, if you are not constrained in timing, we're encouraging to use that on Spot. 1, because of the savings. 2, because you can, if job is failing, because Spot can reclaim the instance and then reclaim the processing that has been it can be rescheduled as well. And you have access to a pool of compute capacity that is pretty large. Now, the key thing of that is really the auto-scaling FME server engine, dynamic engines. And let's go to a demo where Scott is going to show you how it works on a concrete example. Scott?
All right, thank you, Maxime. My name is Scott Bateman, and I'm going to be walking through the actual FME job that was created in FME Workbench and then migrated to FME Server to run distributed among all the different Amazon Web Services EC2 instances that are in the auto-scaling group that we just walked through the architecture for. So this is a relatively complex job. It takes well data as well as municipal boundary data in terms of section, township, and range across the United States. And then it takes stratigraphy details, which in a geology perspective is what formations are at what depth within the earth. And so it does a number of things in here. And so without explaining too much detail on what it does, you can see there's a lot of CPU intensive processes and transformers that are occurring as this job runs. By taking this job and running it for the entire country, it runs for a really, really long time. So what we can do is we can break that up and run it for just specific townships or even specific sections. And then that will allow it to run more quickly and distribute the work among more than one compute resource. So here we are in the AWS Management Console, and I'm going to show Elastic Compute Cloud, or EC2. And this is where the instances that are instantiated will appear. So you can see right now we just have 2 servers that are running, and one is the FME server, and then the other one is a GIS development server, which is what I've logged into here, and I'm showing not only FME, but also we can look at the geospatial data if we would like, the wells and all the different municipal boundaries that it's using to do some of the intersections and transformations. So in addition to the EC2 instances, all of the data is being pulled from and written back to a serverless Aurora PostgreSQL database in AWS. And to pull it all together, we'll use CloudWatch to see what happens as we instantiate the scaled out processing, which is currently set up to run the job every 5 minutes. And I have turned off the FME server automation so that those have been building up, and now we're going to start them to release the floodgates of opening up all of these compute jobs to run in parallel. So the first thing that I want to do is just go over to FME server, and I'm going to turn on this automation, which is watching a simple queue service, SQS set of instructions that are being passed into FME server. So if I go and start this automation, what I'll see is that the number of jobs that are queued, because we have engines running, this was empty before, and it's all of a sudden started to fill up, as well as we should shortly see some of those get picked up by the engines and begin running. So while those are starting up, I'll show that we currently have no engines available at the moment. And then, as Maxime mentioned, we're using the dynamic engine mode, and we have plenty of credits here left to run. So no matter how many we run, I think we should be underneath that number of processing hours. And now we can see that the engines have spawned. And when we go back to look at the jobs, we can see that there are quite a few jobs that have all kicked off, each processing a different state worth of data. And so we've got 1 through 40 that are currently running. For the purpose of flexing the elasticity, we've rerun the same states over and over just to provide a lot of jobs for FME to process. And so we can see that even though it's picked up several, there are still many more queued as well. So now if we go back to the AWS console and we look at the EC2 instances, if I refresh, we should see many FME engines that have started up, and they're initializing as they start to do the work that was handed to them by taking the one large job, splitting it up into smaller pieces, and then beginning to run each one individually. So we can keep an eye on the entire process, whether it's the queue of jobs, the EC2 instances processing the work, or the database. Anything we want to watch in CloudWatch, we can create a dashboard. And so as the jobs start to process, we'll start to see the CPU, network, and disk activity start to peak up. All right, so once this job is completed running, then all of the data is written back into the RDS database, and this shows how we were able to go from just no FME engines running automatically based on the amount of work to continue and spawn new instances based on the amount of work that needs to be performed. And as was mentioned earlier, these can be done using on-demand instances for convenience, or you can also use what we call spot instances for the cheapest compute resources, saving up to 90%. However, there may be a little bit of a delay in starting them up. All right, so that concludes the demonstration of how we are splitting up a job and sending it to many different FME engines, many more than we have in terms of individual FME server licenses. But by using the dynamic licensing model, we're able to just only pay for the hours of compute that we use on those FME engines.
Putting it all together, here we see a solution architecture that builds on the FME desktop-only architecture we talked about in a session yesterday. You can see that we have both an auto-scaling group of FME server using the dynamic server licenses, as well as a relational database for geospatial data, a file server, and Amazon workspaces for FME desktop, all in the cloud, all able to augment your existing geospatial environment. So with that, we will open it up for questions.